Good morning, everyone. My name is Alfredo Sanchez, and my partner is
Albert,
and we created the AA MIPS. So the first thing we're going to be covering is a brief introduction, the instruction set architecture, our enhanced instructions, our hardware implementation, our future enhancements, and finally we're going to leave some room for any comments or questions you guys may have. So first, introduction. Why did we choose AA MIPS?
Well, first of all, both of our names starts with A, and when you think of AA, think of AA batteries.
And not only that, you know, AA batteries is the foundation. They're very basic and versatile. They're very useful. And we wanted to give our clients something that will not intimidate them. Instead, it will want to make them think, oh, this is good, this is useful, this is easy. Like AA batteries are everywhere, you know? So we were like, something simple, fast, reliable, and easy to use.
Who are your clients? Who's
My
the
clients
customer
is
for
anyone
your...
who wants to use a processor that is very versatile, fast, and that is similar to the MIPS with a lot of more enhancements.
So they're going to be simple-minded people?
Not simple-minded, but just to understand that the AA MIPS is not a complicated processor.
Okay.
It's not too different from the MIPS, but it does have enhancements.
Good.
Right, moving on, we're done
Well, what
with
was that little
introductions.
logo at the bottom that you had?
It's a Kausti Lambi. Oh, that's not a logo.
Yeah,
That's
that little saying or whatever that...
Mera katam ho gaya, which in Hindi means I am done. So I'm done with this slide. So
Oh,
we may proceed with the next one.
okay.
So we're done with introduction. We're now going to move on to instruction set architecture. In this section, we're going to be covering the memory structure, the processor register set, the data types, addressing mode.
The instruction set, the instruction formats, and reset.
Right. So in our memory structure, we have the hardware architecture. In our case, we have a MUX that decides whether to use a data memory and I/O memory, or as you can see, we also have instruction memory. So that's what the hardware memory is. Two separate modules, one for program memory and another one for data. In our case, we can only read to the instruction memory. So that's an important thing to note. You cannot write to it. So don't ever try to write because it just won't work. But instead to the data memory and I/O, it does work pretty well. You can read and write. Another thing we also have is the big endian format. So this is the way how the instructions are stored and how data is stored inside our processor. As you can see, the most significant byte is stored in the least significant address, and the least significant byte is stored in the most significant address. And that's what it means to be big endian. Following up, we have a 32Y register that can take in 32 bits. And in this image, as you can appreciate, we have things that are usually used for the registers, like register 0 is always a 0. And we'll be discussing in the reset slide how it's always 0. Register 1, it's the @ sign, and so on. The data types. We have two main data types. The first one is a 32-bit sign integer. To emphasize the point and what it means to be a signed integer, we use the 31st bit in here to signify this number that since it's a 1 in the 31st bit, it's a negative number. In the bottom, we use a 0 to signify that this number right here is a positive number. And I'm showing you right here how the information is stored inside the registers. The next one is the 32-bit unsigned integer. In this case, it could use the whole 32 bits. And whereas the 32-bit sign, it can only range from -2,147,483,648 to the positive value of 483,647. And the unsigned is from 0, no negatives here, 0 to 4,294,967,296.
Can you tell us what instructions use unsigned operands?
The ones that use the unsigned operands.
Yeah, which instructions?
Well, those most likely will be add, subtract, add and sign, subtract and
What do
sign.
you have unsigned? Okay.
You know, and also, in our case, we also use the rotate. you know, we don't, well, no, that's a signed value because it gets shifted. So most likely those are the two main ones that we use.
So you have add unsigned and add, or
Yes.
subtract unsigned?
Yes, we do.
All right, thank you.
Moving on with the addressing modes.
For the addressing modes, we have three main types. We have the register indirect, and the immediate. For the register mode, it's used to access the operand stored in the general purpose registers in the CPU. For the example, we use add. We get the contents of register 1 and 2 and get the operands in there and store the data in register 3. And for register indirect mode, it's also known as the register deferred. We access the contents based off based off the pointers stored in the registers. So for the example, our load word, we get the contents of register S2 based off the pointer. The offset is 4, and we store that, or we load it into register S5. And for our immediate mode, the operand can be specified directly with an immediate value. In our example, we use add immediate. So we add the immediate value 9 to the operand in register 2 and store it into register 1. And our instruction formats are the ArtType, ArtType, and JType. So for the ArtType, we begin with our 6 bits will always be at 0, and our next 5 bits is RS, followed by RT and RD, all of which are 5 bits. RS is our first register source operand, RT is our second source operand, and RD is our destination. Following that is our shift amount, which is also 5 bits, and function, which will tell us which ArtType function we will perform, which is 6 bits. So our next type is the I-type. Unlike the R-type, we don't have an RD, but instead we have a 16-bit immediate value. So whatever, that's a typo, whatever our data or whatever calculations we perform will be stored in RT instead of RD. And then our last type is the J-type instruction. So the first 6 bits will be our opcode, and following will be the 26-bit immediate value telling which address to jump to. So for our R-type instruction set, we have the baseline instructions starting from the shift left logical, going all the way down to break and set interrupt enable. Our next is the I-type instructions. We have the branch equal all the way down to the store word. And the J-type instructions, which is the unconditional jump and the jump and link. For our enhancements, we have the required input, output, and return interrupt. For our additional instructions, we added the load byte, load half, store byte, and store half. And additionally, we added our enhancement keys, which allow us to perform our other enhanced instructions, or enhanced instructions. So we added the shift left arithmetic and the rotate right and rotate left. They both act as an R-type, but instead we just use the E key to perform these functions.
So in the R-type, the opcode is all zeros. And whereas the E key, it's, I believe, 1F.
Right.
Right. And it's the same thing. If the opcode, as soon as it's V1F, the other format, it knows it's like just like an R-type.
Right.
So for reset, as stated earlier, our register 0 will always have 32-bit 0, and for our stack pointer, which is register 29, the value will always be 3FC hex.
And this value is imperable. It's really needed for the jumps and jump and links and the return from the interrupts. If we don't have this value, the machine will not work properly.
What value?
The 3FC, so stored at the reset state to register 29 for the stack pointer.
What do you mean for the jumps?
Our initials.
Our initialization.
But the jump, what does the stack pointer have to do with jumps?
Well, it had to do with the jump and link. Jump and link. I said jumps, but I meant jump and link.
Jump and link, it stores it on the stack?
No, but it uses the 3FC value just to be able to reference it.
Jump and link?
Just as a reference, as a number.
Are you sure?
At least in my machine it does. But it's just a reference, it doesn't use it for anything else. And it works pretty well.
What do you mean on jump and link, it uses it as a reference?
Well, I store data into the register 29, so I can then recover it later.
Okay.
So now we're done with this.
Let me go back to
Section?
that. So I'm to understand that jump and link doesn't use the return address register.
Okay.
Is that correct?
Well, it's just, since I have to return to a previous value.
Right, but the
So
MIPS
PC
stores the return address in the return address register
which is
on
the
jump and
31.
link. Yeah.
Yes,
So do you do that or you don't do that?
I do that as well. But just for purposes that we might need it later.
Oh, so it's like you stored it in both places?
Yeah, pretty much.
Okay,
It's like a type of enhancement for
Good.
future programmers. that
okay,
use it.
okay.
I apologize for not making that a little
No,
more
that's
clear at the
good.
beginning.
That's why we're here.
Perfect. Now we may move on to the enhance instructions. So in our enhance instructions, we have the input output, the return interrupt, the load byte, load half word, store byte, store half word, the barrel shifter, the rotate right, and the rotate left. So the first thing is the input output. These instructions just work just the same way as load and store. And as we shown in the first diagram, we have a data memory, and then we have an I/O memory, and that's where this is used. The return interrupt. This is an instruction that once the ISA is finished executing, it uses this instruction to jump back to the program counter and where it was first interrupted at. The load byte. The load byte is just 8 bits, and since it's just a byte, whatever address you set it to, that's where it's going to get stored. But something that is very important to notice is that the registers are not byte addressable. They're 32 bits wide, so you have to load the remaining bits with zeros. And as you can see in this section right here, we load 31 to 24, 23 to 16, 15 to 8 with all zeros, and then the memory, and then 7 to 0 to whatever the data is. The load half word is the same way. The only difference is that this is 16 bits. So the first half word, 31 to 24 and 23 to 16, must be loaded with zeros because the registers are not byte addressable. The store byte.
Can you go back there, sorry, in context? Where is this implemented, this case statement?
This case statement is implemented inside our data module.
Okay, so it's your memory module.
Your memory module.
Okay,
yes.
that need to be made clear.
And
So,
we do have another signal that comes in as the load type.
very important.
And that determines whether if it's a word, half word, or if it's a byte.
So that's hardware enhancement. That's how they did that.
Yes.
That's a big change. Excellent.
Thank you. Oh, sorry. Stored byte. The beauty about the storing byte is that it's a byte addressable, so we don't have to worry about the remaining 26 bits. So whatever address you tell it to store it at, it stores it right there.
Right.
To store half word, the same concept applies. Since it's byte addressable, you just got to reference like the big Indian format. 15 to 8 will be stored in the least significant address, as shown right here. And 0 to 7, which is the least significant byte, is stored in the most significant address. Rotating right. This is just one big case statement, as
Sure.
you can see right here. So there's not much to it other than just making sure that you're putting the bits in the proper order. And we do have the benefit of rotating up to 31 times. The rotate left is the same concept. It's just one big case statement. And depending on the shift amount, that's the amount of times we rotate. The barrel shifter. We were able to enhance the shift left, shift right, and shift arithmetic by being able to expand the barrel shifter to up to 31 times based on the shift amount that is designated. And again, just like the rotates, it's just one big case statement. And as you can see right here, this is the mux we utilized in order to make our barrel shifter work properly. So if it was 0C, then you're going to shift left logical. If it was a 21, shift right logical. If it was a 0E, then it's shift right arithmetic. And if your function select was 20, then it was shift left arithmetic. If your function select was 22, then it's rotate right. And finally, if your function select was 23, then you rotate left. And as you can see right here, these are the modules that we utilize in order to verify that our machine worked. Initially, we first loaded data onto the registers, all the way from the Louis and Oris, as you can see up there. And then we use the rotates right from line 6 to 9. We rotated right. At this moment, we cannot prove to you these values because we use calculators in order to determine the big rotations. But if after the presentation, if you would like to verify these values, I'm more than glad to show you my calculator that I use to verify the verification. And same thing for the stored byte. The stored byte is a little bit more simple to prove that it works. Because as you can see, I'm telling the MIPS to store the data from register 1 onto the base address 15 with 0 offset. So for register 15, the base address is 0C0. So let's navigate to 0C0. So the data memory right there is 21. But the register for register 1, what's the least significant bytes that you see there? On 0x1, it's a 21. And as you can see, and data memory 0C0, it's a 21 as well. The next one, get the contents from register 12 and store it onto base address 15 with offset 8. So again, address 15, base address is 0C0. So let's go and let's say register 12. Register 12 happens to be C. So it should be 8866. So let's go to the offset 8. So then, since it's storing a byte, it's just 66. Moving on. Now we're going to store half words. Now I'm telling the MIPS machine, grab the base address 15 with offset 4 and store the contents of 11. So what's contents 11? Let's go to B. It's BB22. And now let's see if it's storing it with offset 4. There you go. BB22. C4 contains the least significant half word of register 11. Moving on to the next instruction, store half word, which is base address 13 again, offset 0C, and store the data of register 13. So let's register 13 happens to be 7744. So what's 0C0 plus offset C? CC. So what's CC? 7744.
When showing us, Alfredo, go back to the
Yes.
focus on data memory.
Yes.
You're showing us addresses on the left, C0, C4.
Yes.
Is the 21 at C0 or is the 21 at C3?
The 21 right here is from the register 3.
No, just orienting, I don't know.
Oh, I see.
You've got 4 bytes across there. Which one is the least significant?
The
Which
least
one?
significant is the one to your left.
Okay,
And
so
the
it
most
goes
significant
0,
goes to
1,
the
2, 3.
Yes.
Okay,
Yes. Moving on with the next instruction is the load bytes. Now I'm telling the MIPS processor, load onto register 5 the content of base address with offset 8. So 15 again is 0C0. And the offset is 08, so it's C8. And it should be stored loaded onto register 5. So C8 happens to be 66. Now let's check register 5, which is 66. Next, now I'm telling the MIPS machine, load onto register 3 with offset base address of 15, and offset is 0. So then that's C0, and that's 21. And what's register 3? 21. Now the load half word. Now I'm telling the MIPS, register onto register 4, load onto register 4, C0 with offset 4, so C4. So let's see, what's C4? C4 happens to be BB28, and register 4, BB28.
22.
I'm sorry, 22. Next one, same thing. Load onto register 6, base address C with offset C, so that's data memory CC. Data memory CC is 7744, and we said load it onto register 6. And what's register 6? 7744.
Okay.
Now moving on to the hardware implementation.
Alright, for the hardware implementation, we just incorporated, or we're just showing the block diagrams to give you a general idea of what we did in our code. So this is the overall design. So we have the overall CPU, which includes the instruction unit, integer data path, and MIPS control unit. And using the Harvard architecture, our data memories, or our input-output memory as well, is separate from our instruction unit, or instruction memory. And this is the overall flow of how each module connects to each other. So the input and output memory and data memory are wired to the MIPS control unit, similarly to each other. And our instruction unit is the same. We did not make any enhancements there. So our PC mux goes to the PC register, and it goes to the instruction memory, and then it goes to the IR register, which outputs to the integer data path, and it also sign extends to the integer data path as well. For the integer data path, we have the DMUX controlling what destination register it goes to. Register 29, the stack pointer. Register 31, the return address. Register RT, which is IR 20 to 16, and RD, which is IR 15 to 11. And for the TMUX, we have data coming in from the instruction unit, the sign extend, or we're taking in the T address, or PCN, or the flags register. So we added the SMUX to for our stack pointer, which is 29, and it'll be stored into RS. And the rest will flow
Shift
into,
right.
it'll go to the barrel shifter, and if it's any other function, then it will come from the MIPS, and then multiply and divide will be 1F and 1E.
So moving on is our future enhancements. For the future, we would like to implement a more versatile and more complex system, in where we add a floating point unit a vector unit that makes 64 bits. Now these days, everything is 64, at least a great majority of things, and a quad core. So divide up the work and speed up the process. Finally, comments, questions, or concerns you guys may have?
Very good, thank you very much.